Welcome! Let's talk about the secret decisions happening inside all of our devices. In this explainer, we're going to pull back the curtain on the fundamental building blocks of, well, the entire digital world. I'm talking about these tiny, completely invisible components that are making billions, billions of decisions every single second, right inside the very device you're watching this on.
So, let's start with the big question. We all kind of get that our digital world runs on zeros and ones, right? On or off, simple as that. But how do you get from that basic on-off signal to, well, playing a video or sending a message or doing some super complex calculation? How do these simple little states actually translate into all the amazing things our devices do?
Well, the answer lies in something called a logic gate. And the name is actually perfect. Just like a gatekeeper, it controls what gets through. A logic gate is basically a tiny little electronic circuit. It takes in one or more of those binary signals, a 0 or a 1, and based on a very specific rule, it spits out a single output signal. It's the most fundamental decision maker there is.
So, here's how we're going to break it down. We'll start with the three most basic gates. Then we'll meet the so-called universal gates, which are pretty cool. After that, we'll look at some special gates that check for differences. And finally, we'll see how all these simple pieces get put together to create some really incredible complexity.
Okay, let's dive right in and meet the three absolute cornerstones of all digital logic. This is your basic toolkit: the AND gate, the OR gate, and the NOT gate.
First step is the AND gate. You can think of this one as the really strict gatekeeper. It has a super simple rule. It will only output a 1, an ON signal, if every single one of its inputs is also a 1. If even one of those inputs is a 0, then the output is 0, no exceptions. The light switch analogy here is perfect. If you've got two switches wired up one after the other, you have to flip them both on for that bulb to light up.
To really see how this works, we use what's called a truth table. It's basically just a cheat sheet that shows every possible input combination and what the output will be. And for the AND gate, it's crystal clear. You only get a 1 on the output when input A and input B are both 1. Every other combo, you get a 0.
Next up, we have the OR gate, and this one is way more relaxed. Its rule is simple. The output is 1 if input A is 1, or if input B is 1. Really, if any of its inputs are 1. The only way you're getting a 0 out of an OR gate is if all the inputs are 0. Think about light switches wired in parallel. The electricity has more than one path, so flipping just one of them is enough to turn on the light.
And again, the truth table for the OR gate just makes it so obvious. Look at that. The only time you see a 0 in the output column is when both inputs are 0. If there's a 1 anywhere in the inputs, the output is always a 1.
And rounding out our basic trio is the super simple but incredibly important NOT gate. People also call it an inverter, and that's exactly what it does. It takes one single input and it just flips it. A 0 goes in, a 1 comes out. A 1 goes in, a 0 comes out. That's it. So simple, but so powerful.
So you might be wondering, how many rows does a truth table need? Well, there's a really easy formula for that. It's just 2 to the power of n, where n is the number of inputs you have. So for a 2-input gate like we've seen, that's 2 squared, which is 4 rows, or 4 combinations. If you had a 3-input gate, it'd be 2 to the power of 3, which is 8 combinations. Simple.
All right, now that we've got the basics down, let's look at two really special gates, the NAND gate and the NOR gate. They're known as universal gates because, as you're about to see, they're like the master builders of the digital world. The NAND gate is pretty much what it sounds like. It's a NOT AND gate. Just imagine you take the output of a regular AND gate and you feed it straight into a NOT gate. That's a NAND gate. It gives you the total opposite result of an AND gate. This means the only time a NAND gate outputs a 0 is when all of its inputs are 1.
And you can probably guess what's next. The NOR gate is a NOT OR gate. Same idea. It's an OR gate, but with its output flipped. It only gives you a 1 in that one single case where all of its inputs are 0. Any other time, the output is 0.
Now, this is why they're called universal gates, and it's actually a pretty mind-blowing concept in electronics. It means that if you have a big enough box of just NAND gates, or just NOR gates, you could build any other logic gate you want. And if you can build any other gate, you could, in theory, build an entire computer. It makes the whole manufacturing process way, way simpler.
Okay, on to two more specialized gates that kind of act like judges.
Their whole job is to look at their inputs and tell us if they're the same or if they're different. These are the exclusive OR and the exclusive NOR gates.
And they have a very clear division of labor here. The XOR gate, that's exclusive OR, and outputs a 1 only when its inputs don't match, like a 0 and a 1. So you can think of it as an inequality checker. The XNOR gate, exclusive NOR, does the exact opposite. It outputs a 1 only when the inputs are identical. So 0 and 0 or 1 and 1. It's an equality checker.
And when you see their truth tables side by side like this, it just makes the relationship so obvious. Their outputs are perfect opposites. Wherever XOR is a 0, XNOR is a 1, and vice versa. It really highlights how they have these perfect complementary jobs.
So now we have all these simple little building blocks. The big question is, how do they combine to create the incredibly complex functions our devices perform every day? Let's actually see it in action by building one of our exclusive gates using just the basic ones.
Okay, this formula for an XOR gate might look a little intimidating at first, but it actually reveals its own secret. If you look closely, you'll see all the symbols we've been talking about: the dot for AND, the plus sign for OR, and that little bar over the letter for NOT. This formula isn't just math, it's a blueprint. It tells us exactly how to build an XOR gate with our basic toolkit.
And here's how we'd actually build it, step by step. First, you'd use a couple of NOT gates to get the flipped versions of our inputs. Then, you use 2 separate AND gates to build the 2 halves of that formula. Finally, you take the outputs from those 2 AND gates and you feed them into one single OR gate. And guess what? The output of that final OR gate is exactly the same as a dedicated XOR gate. We built it from scratch.
And this just perfectly illustrates the core principle of all digital electronics. It's all about combining these incredibly simple, predictable components and rules to achieve unbelievably sophisticated results. From just a handful of basic gates, we can build circuits that add numbers, circuits that store memory, and circuits that run entire operating systems.
So, at the end of the day, here's the crucial point. Every single action you take on your phone, your computer, every tap, every swipe, every click, it all gets translated into this massive cascade of binary signals, flowing through billions of these tiny, simple decision makers. It's just a powerful reminder that the most amazing complexity is often built from the absolute simplest of ideas. It makes you wonder, what will they decide next?